All right, now we're going to continue the projectile motion example from lecture A. We are now on slide 3. This is a projectile traveling along a parabola. And we just saw at the end of lecture A, the formula for the distance traveled is very complicated. Can I find the distance, the total distance, by the time it hits the ground? That's the next thing I want to address. This is not the same as that horizontal range. It's not the number that we found was about 22 kilometers. Its distant b, where b is 250 over 4.9. It's bigger than 22 kilometers, it's about 23 kilometers. Because it's traveling not along a straight line, but along a parabola. A very long parabola like this. Actually, the parabola is only about 1 kilometer longer than the horizontal line. If you look at it graphically and make the scales the same, it will be because it looks like a very wide parabola. Visually, it'll be very close to the horizontal line. Okay, and again, I use technology to do that. Here are graphs of these functions. By these functions, I mean the speed and the distance traveled from the end of lecture A. The graphs actually don't look that wild, even though the formula was wild. In fact, the distance traveled was the really wild formula involving the inverse sinh function, but its graph looks basically straight. There it is, blue graph in both pictures. This is the same graphs, just in 2 different windows. Distance is blue, speed is red. The units are different. The distance units would be meters. The speed units would be meters per second. This one looks horizontal, but it's not. You look closer, it's actually like this. Kind of looks like a parabola, but it's not because it's a square root of a parabola, actually, which is not a parabola. It does have a minimum, which should make intuitive sense halfway along the time interval to the end. I forgot what b was, 50 something? 250 over 4.9. I forgot my calculator, except my phone, 250. About 51, really close to 51. The minimum is going to occur really close to half of that, 25.5. Right around there. That'll be the minimum speed of around, hey, 433. Yeah, that 433 is the constant horizontal component of the velocity vector. At the peak, that's the only component of the velocity vector, because the velocity vector points straight to the right when you're at the peak. In general, the velocity vector goes like my finger's going here. When you're at the peak, it points straight horizontal. It's got no vertical component. And so the speed is its length at that moment, which would be 433, approximately. And over a closed interval, the maxes occur at the endpoints. Speed of 0 would equal speed of 51 or so, which is around, well, 500. Yeah, it's got to be 500, actually, because that's the initial velocity. That was the length of the initial velocity vector. The red is the derivative of the blue, the slope of the blue, which is not constant. This looks straight, but it's not. The red graph is decreasing here. That means the slope of the blue is decreasing. It's ever so slightly concave down. You just can't see it. Then the red graph's increasing over here. So the slope of the blue is increasing. It's got to be ever so slightly concave up. Amazing that such an ordinary-looking graph could have such a complicated formula, but it does. All right, on to our last main application for the course. Data modeling with density curves and integrals. Just got a bunch of examples here. I want you to think about these examples intuitively, and then we will relate them to calculus at the end of each slide. I got some data. Don't write those numbers down, okay? Don't write them down. I'm not going to write them down. I did take the time to type them all. Where did I get these numbers? Well, I did a simulation in Mathematica. I didn't actually look up some numbers somewhere. Pretend this comes from some application. Bunch of numbers. we might want to plot those data points. How? There's various ways to do it. One of the more common ways is called a histogram. If you've taken stats in the past, you should have learned about histograms. I don't want to do that. That's too complicated for our purposes. I want to do something simpler. I just want to plot these numbers on a number line. Make a dot plot like that. There they are. There's 50 of them, though some of those dots could be so close together that they might look like one dot. So they could be, if you actually count them, it could be less than 50 visually. What can you say about this? Notice there's no obvious pattern to where the data are most dense. I mean, yes, there's spots where it's denser than other spots. Pretty dense right here and right there. Dense, like how close are the points together. Kind of dense right there. Not so dense, say, here and here. But there's no obvious pattern to the density. And in modeling this with a density function, we want to keep things as simple as possible. And because of that, the simplest thing to do here is to use what's called a uniform distribution. The data are basically uniformly dense. A density curve or density function with a constant height would model this uniformity. Talk about what that means here as we go. This would be what's called a uniform distribution. It's going to be a function whose height models the density. This function is going to be higher when the data are more dense and lower when it's less dense. However, because there's no clear pattern, we're going to take a constant height. But what should that height be? You want to choose it, the height, so that the total area under the density curve is 1 or 100%. So notice the data is between 0 and 10 here. I want my density function or density curve to be a horizontal line where the area under the horizontal line is 1. Which means it's got to be a finite horizontal line, a line segment, above the interval from 0 to 10. That's my domain for this function. It's just 0 to 10, because that's where the data is. Or where the data are, I should say. Data or data is a plural word. Datum or datum is a singular. Well, hey, wait a minute, that's a rectangle. Area is base times height. Base is 10, the height's got to be. Come on, finish it. 110. 0.1. Why do we want its integral to be 1? So here's the picture of the graph. Why do we want the integral of that to be 1? Because what we want is we want another function, an antiderivative of this function, that gives the accumulated percent of points below the given value of x. I want to make another function. So this is like little f of x. This is my density function. I'll call it just df for short. I want to make another function that's an antiderivative of this. Antiderivative. It's got to have a constant slope of 1/10, so that its value at any value of x gives the approximate percent of the data points less than that value of x. You got to start it at 0 if that's going to happen. Capital F of x, it's an antiderivative of little f of x. It's got a slope of 1/10. That would work because, for example, once you're up to x equals 10, the percent of the data points less than 10 is 100%, 1. Right? Percent means per 100. So 1 is 100% because 100% means 100 divided by 100. 50% means 50 divided by 100. Percent means per 100. Does it work for other values of x, like say x equals 3? The value of this function at 3 would be 0.3 or 30%. Is 30% of the data less than 3? What would 30% of 50 be? There's 50 data points. 15. Are there 15 data points less than 3? Not necessarily exactly, but it should be close. 1, 2, that might be 2 data points there. Kind of looks like it could be 2 points together. I will assume it is. I could look at the numbers as well, just try to double check. But actually, 0 occurs twice as well. There and there. Okay, I got to count this one twice. 1, 2. I think this is going to be 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We're getting close to 15 here when x is close to 3. What percent should be less than 5? The value of the CDF, this is a CDF, cumulative distribution function, is 50%. It should be about 50% of the data. 25 points should be less than this point here, approximately. We were up to counting like 13, 14, 15 here, 16, 17, 18, 19, 20 or so, 21, 22, 23 maybe, or 24 if I missed a point. Yeah, about half the data points is less than 5. So the density, the height of the density function tells you how dense the points are. And again, there's no pattern, so we're using a constant density here. The CDF tells you the percent of the data less than the given number. Let's do another example. More data. Nobody, including me, likes to just look at a bunch of numbers. Well, maybe I like it more than your average person. But yeah, a list of numbers. It's more informative to graph it. Although one pattern I do quickly see here before I graph it is there seems to be more small numbers here than big numbers. And here's a graph that confirms that. There's the dot plot. The data are a lot denser in the small numbers than in the large numbers, though the large numbers do occur once in a while. We would want our density function, our df, to be high when x is small and low when x is big. Maybe a straight line, or maybe an exponential decay? I don't know. Data are clearly most dense near 0. There is asymmetry in the density. This uniform one is symmetric, centered on 5, and the area on either side of 5 is the same. This one's going to have, it's got asymmetry. More dense here, less dense there. The density curve would be high on the left and low on the right. Because of that, it's actually called right-skewed, because it's got a long right tail. Is how statisticians think about it. The density might look like this. And you've got a long right tail. It's like it's an animal, and that's a tail. And because it's got a long right tail, we say it's skewed right, even though most of the data is on the left. It's easy to get confused by that. There's some high outliers in right-skewed distributions. Yeah, this is commonly modeled actually by an exponential decay function that I hinted at. Now you could use a straight line as well. There are lots of different, there's really infinitely many choices you can make. Some simpler than others. You want to keep things simple. This is modeling, it's not perfect. It is modeling that you might say is not very, what's the word? It's just looking at the data. It's not thinking about bigger issues about where does the data come from. Simplistic approach, you might say. Actually, with machine learning, for the most part, machines have to do things simplistically, right? The machine can't think about it, what would make sense here? No, it's just got to use simplistic models of the data. Humans do have an advantage over machines in this situation because we can think about what would make sense here. Could I reason out why the density function looks like this? And by the way, this applies not just to data, it applies to lots of things. And in Calc 2, you apply this kind of idea to lots of things, including, say, density of bacteria along a line. More dense there, less dense there. Or density of a wire that's made in a funny way that makes it denser over here than it is over there. Talking about mass density. Okay, so there's lots of applications of this idea besides data. So here's an exponential decay function that models the data reasonably well. I'm not claiming it's perfect. Actually, it is in a sense it is perfect because this was the function I used in Mathematica to do the simulation that gave me the data. So I kind of cheated in a way. I work backwards. Does it go down to 0 there at 1? Actually, no. It is exponential decay. It never actually reaches 0. It actually goes on forever. But I'm sort of ignoring the part past 10. What's the CDF, the cumulative distribution function? It's got to be an antiderivative of this. And since the data started at 0, it's got to go through 0, 0. Integrate this exponential decay. And think of it as a definite interval from 0 to x here now instead of t, say, of an arbitrary exponential decay, e to the negative k u du, say, where u is just a dummy variable, doesn't mean anything. Using the fundamental theorem of calculus and a little bit of experimentation, I could write this. Where did I get that? A little bit of thought, realizing that if I differentiate something like this, I'm going to get this. Derivative with respect to x, or with respect to u, of negative 1 over k, e to the negative ku, is negative 1 over k, that comes along to the right by linearity, e to the negative ku, and then by the chain rule times an extra factor of negative k. And then the k's cancel, the negative signs cancel, this simplifies to e to the negative ku. There's an antiderivative of the integrand. Evaluated u going from 0 to x. I'm using the fundamental theorem of calculus now. I plug in the top limit in for u. Subtract what you get when you plug in the bottom limit for u. The bottom limit is 0, so I get an e to the 0. E to the 0 is 1. 2 minuses give you a plus. This is plus 1 over k. And you simplify it. And so the whole function simplifies to, you can factor the 1 over k out if you like, 1 over k, 1 minus e to the negative kx. And that would be your CDF, if you know what k is. I think the k for this is 1/2 actually. The k is 0.5. And that is a function whose graph goes to the origin. Plug in x equals 0 there. E to the 0 is 1. 1 minus 1 is 0. It does go through the origin, and here's what it looks like. Now again, technically, because this graph never touches the axis, this graph actually never quite reaches 1 or 100%. But it gets really close. And you use it in the same way as we use the other one. If I want to know the percent of the data, that's, say, less than 3. Let's do 2 instead. Go up to the CDF and find its value there. It's about 0.6 or 60%. About 60% of the numbers should be less than 2. 60% of 50 is 30. I should get about 30 points right there. I'm not going to try counting them. They're pretty dense. There's probably a lot of overlap there. 2 or 3 points that look like 1 point. Might be better to count the ones that are bigger than 2. There should be 20%, what? 40% of those. 20 out of 50. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, it's not doing so well. Unless there's repeats in here. You can look at the numbers themselves to see that. And these things don't improve. They are just models. Keep going. Slide 3. 2 more examples. We can do it. We've got 9 minutes here. Question?
Can you model the data with histograms as well?
Yeah, you can do histograms. And the density actually kind of follows the histogram. I just don't want to talk about histograms because it would take us too far afield. But yes, the density basically follows the shape of the histogram. Another data set with 50 points. Don't want to look at all those numbers to see patterns. I want to plot them to see patterns. Look at that. Now our data is most dense in the middle and less dense on either side. Basically symmetric. But now I don't want to use a uniform because it's definitely more dense in the middle. Clearly the data are most dense in the middle, near 5. There is symmetry in the density again because on either side of 5, the density goes off at approximately the same rate. So I'm hinting at a curve that looks like this here. Bell-shaped curve? Yeah, it's called a normal distribution. Also called a bell-shaped curve or a Gaussian distribution, after Carl Friedrich Gauss. Gauss is famous for a lot of things, right? Gauss is some unit of electricity and magnetism. I also decided I wanted its mean, its average to be 5, and its standard deviation to be about 1.7. Don't worry about what standard deviation means. And I chose this density function. Centered at 5. A certain amount of spread to it that gives the standard deviation to be 1.7, but don't worry about what that means. It is highest when the data is most dense, and lowest when the data is less dense. Actually, just like the previous example, this one goes on forever and ever without touching the axis to the right, and even to the left. This never reaches 0, so this is not graphing it over the entire real line. I'm just ignoring the parts that are bigger than 10 or less than 0, where x is bigger than 10 or less than 0. And here's the DF. And it looks like it goes to the origin there, but technically it doesn't. It would go toward 0. Oops. Never quite reaches 1. It looks like it reaches 1, but it's just getting really close. It's asymptotic. Once again, I can use this to say, for example, about 40%, if x is 4, about 30% of the data should be less than 4. I'm going to go up to the blue graph. That's how I figure out the percentage. That's the main conceptual thing I want you to realize, that you can test them. To figure out the percent of the data is smaller than some number, you go up to the blue graph and find its value. It gives you the percent. By the way, these percents can be thought about as probabilities as well. The probability that the next data point is less than 4 is going to be about 30%. The probability that the next data point that I gathered is less than 6 will be about 75%. Okay. One more example. This one's the most subtle. Here's the data, and here's the graph. Now I made the data densest near 2 or 3 or 4 or so. Not near 0 like the exponential one was. But this is not symmetric either. It's definitely denser in the lower regions than the higher regions. Now, a pretty simplistic one you could try would be maybe a density function that looks like this, perhaps. That certainly could work, though it's not how I generated these data. I use something called a gamma function. And this is the most common thing to use in this situation. What's a gamma function? Gamma density. I don't want to get into it. It's complicated. Okay. Actually, the function itself is not a gamma function. It's just, it uses something called a gamma function. And here's what the graphs look like. there's the density. The graph is highest near 2. That's technically where it's most dense, even though it's pretty dense in near 2. Antiderivative going through the origin will be the cumulative distribution function, the CDF. And once again, the main conceptual point, well, the main conceptual points I want you to know are that the DF, the density function, the red graph, is the derivative of the blue. The blue is an antiderivative of the red. The density graph is highest when the data are densest, lower when the data is less dense. And to find the percent of the data less than any given point, like 4 here, or the probability that your next data point is less than 4, you take that value of x and go up to the blue graph, up to the CDF, to find the value, in this case about 0.8. To say 80% of the data or so are less than 4. Or maybe you say less than or equal to 4. Doesn't really matter. These are all approximations anyway. The probability that the next data point will be less than 4 is about 80%. Okay, so it's those conceptual points that I want you to understand. And we actually finished early. Have a good weekend.